So think about this for a second. Powering an entire city with just a handful of metal rods. I mean, no smoke, no fire, definitely no fossil fuels, just the raw, incredible power that's locked deep inside the atom. It's wild, right? Okay, so let's dive into the science behind one of humanity's most concentrated and, yeah, most controversial sources of energy.
And no, this isn't some kind of science fiction. It's the reality of nuclear power. So today, we're going to break down exactly how this whole thing works, from the tiniest and possibly small atom all the way up to the electricity that's, powering our world.
All right, so the whole concept of nuclear energy, it really just hinges on one single fundamental process. And this is something that happens at a scale so small we can't even see it. It's a process called nuclear fission. So here's how it works. You have a neutron that slams into a uranium atom. That atom splits, and when it does, it releases this massive burst of energy. But, and this is the really crucial part, it also releases more neutrons. And what do those neutrons do? Well, they go on to split other uranium atoms, which release more neutrons, which split more atoms. You get the idea. It's this incredible self-sustaining chain reaction. This cascade of splitting atoms is what generates the mind-boggling amount of heat that powers the entire plant. Now, it might sound a little too simple, but it's totally true. At its heart, a nuclear power plant is really just a very, very sophisticated way to boil water. Seriously, just like a coal or gas plant, the end goal is to make steam to spin a turbine. The huge difference, the game changer, is the heat source. Instead of burning stuff, we're harnessing the energy from splitting atoms. Okay, so this diagram, this shows us the whole process in one shot. What you're looking at here is a pressurized water reactor, or PWR. This is the most common type of nuclear reactor on the planet. So let's break down how this incredible machine takes that atomic energy and turns it into the electricity that keeps the lights on. All right, so we've got the what of fission down. Now let's get into the how. We're going to go right inside the heart of the plant, the reactor core, and it's all tucked away inside that super thick, concrete containment building. So right at the center, you've got the uranium fuel rods. That's where all the action is, where the fission is actually happening. Then, woven between them, you have the control rods. You can think of these as the brakes for the whole system. They're like sponges for neutrons. So by raising or lowering them, operators can control the speed of that chain reaction with incredible precision. And the whole shebang? It's all housed inside that massive steel-reinforced containment building, which is basically the ultimate safety shell. Okay, so we've got this controlled chain reaction, and it's generating a ton of heat. The big question is, how do we turn all that heat into the electricity that, powers your phone? Let's follow the energy on its journey. First up, that heat from fission gets a closed loop of water incredibly hot. We're talking over 325 degrees Celsius. It's under so much pressure that it can't even turn to steam. Now that superheated water gets pumped over to boil a completely separate loop of water. That second loop flashes into a powerful jet of high-pressure steam. That steam is what blasts against a massive turbine, spinning it like a giant pinwheel. The turbine turns the generator and boom, just like that, the power of the atom is flowing into the grid. But this always leads to the big question, right? The one that's on everyone's mind when we talk about nuclear power. What happens if something goes wrong? I mean, generating this much power, it comes with a huge responsibility to keep it under control. Well, nuclear plants are designed with layer after layer of safety systems. And probably the most critical of all is the ability to shut the whole thing down instantly in an emergency. It's called a scram. And what that means is that those control rods, the neutron sponges we talked about, are slammed down into the reactor core in just a few seconds. This completely stops the fission chain reaction cold. It is the ultimate off switch. But, and this is a really big but, stopping the fission is only the first step. Yeah, here's the critical twist. Even after you hit that scram button and stop the fission, the reactor core is still incredibly hot. It keeps generating about 7% of its full power. Now, this isn't from splitting atoms anymore. This is something called decay heat. It's the leftover energy from all the radioactive byproducts. Now, 7% might not sound like a lot, but trust me, 7% of a massive reactor is still an enormous amount of heat. And that heat absolutely has to be removed. And this right here is the absolute heart of what went wrong in the major accidents we all know about. At places like 3 Mile Island and Fukushima, the SCRM systems actually worked perfectly. The chain reactions were stopped. The disaster wasn't some kind of runaway reaction like in the movies. It was a cooling problem.
They simply lost the ability to get rid of that lingering decay heat, and that is what led to the core meltdowns. And this is probably one of the most important things to get about reactor safety. A meltdown that's caused by decay heat is a slow-motion overheating event. It is fundamentally completely different from a runaway chain reaction. It cannot cause a nuclear explosion. The challenge, the whole ballgame, is making sure those cooling systems always work, no matter what. You know, these hard-learned lessons have driven some really incredible innovation in reactor design. So let's take a look at how this technology is evolving, how it's getting smaller, safer, and even more efficient than ever before.
Okay, one of the most promising ideas out there right now is something called the Small Modular Reactor, or SMR. So instead of these massive, one-of-a-kind projects that take decades and billions to build, think smaller, standardized reactors. They're built in a factory, kind of like a car, and then assembled on site. This makes them cheaper and faster to build. And the coolest part, many of these new designs have what's called passive safety features, meaning they can cool themselves down using just things like gravity and natural convection without needing any outside power or even a human to flip a switch. And they're not just smaller and safer, they're often way more efficient. So, take a look at this. A typical reactor today converts about a third, 33% of its heat into electricity. Not bad. But some of these advanced SMR designs can push that efficiency all the way up to 45%. That is a massive leap. You're getting so much more clean power out of the same amount of fuel. And if we look even further down the road, researchers are exploring some truly game-changing ideas. You've got things like thorium reactors, which would use a fuel that's way more abundant than uranium and creates a lot less long-lived waste. And then, of course, there's the holy grail, nuclear fusion. That's where instead of splitting atoms apart, you're smashing them together. It's the same process that powers our sun. It's ridiculously hard to do, but if we ever crack it, well, it promises basically limitless clean energy. So all of this leaves us with a huge question for our energy future. You know, our global demand for clean power, power that's on 24/7, rain or shine, is just getting bigger and bigger. Nuclear technology is a powerful solution on the table, but it demands incredible engineering, a rock-solid commitment to safety, and of course, public trust. So the real question is, can these next-generation designs finally deliver on that promise? At the end of the day, the story of nuclear power is really one of incredible potential and profound responsibility. It just goes to show you that hidden within the smallest things in the universe is a power great enough to shape the entire future of our planet, if we can just learn how to control it wisely.